Hello, Justin.
Hello.
How are things?
I'm not too bad. How are you?
Yeah, same, I think.
Yeah.
Managing well. I did post the exam by any chance if you've seen it.
Oh no, I haven't been on the site recently.
Okay, yeah, so I think, yeah, I'll talk about that today. Let's wait for Angela. How is the internet
That's good.
for you?
Yes, I haven't had any
Are
issues.
you taking any other class?
Not like in regular class sessions. Like the only other course that I have is independent study that I was doing with Ishari, and Messiah was also in there with me. So that's it. But we're not actually like meeting at a scheduled time or anything. She's having me develop a PowerPoint for the next couple chapters that we were going to go over, and that's just I guess that's how we're going to do it for the rest of the semester.
Okay.
How are your undergraduate courses going? Are they going smoothly as well?
Oh, no, they're going as usual, actually. I'm able to do it. It's just I lost a week because of the
Right.
extended spring break. Otherwise, this has not really affected it too much. Yeah, I think in the first week I was a little, I would say, off the usual because of the change. But otherwise, now I got used to this and I'm able to maintain the routine. Yeah. Yeah, so I would say it has not changed anything. Yeah, we're behind for sure. 1 week because of the in all the courses, including this one. 1 week because we lost a week, but then here and there you lose a little bit. So I would say I've lost 2 weeks in a sense. I'm behind by 2 weeks, but yeah, reasonable. Like I would say, usually you're behind by a week in a semester. So this is you're behind by 2 weeks. So not that as bad as it could be. Yeah, for the kind of changes that's happening. So I'm pretty satisfied the way it is going. Yeah, of course, it can be a lot better the way it is than what we are doing.
Right.
But yeah, I'm able to achieve things. Yeah. So, like I heard from other colleagues, like most of them are just using Zoom and writing and basically recording it.
Right.
But it seems like it is going, and many are facing problems with the internet. Luckily, I'm not having that problem. I can imagine that if the internet goes bad, then all this will crumble down.
Right. Yeah.
Yeah. So it depends a lot on the internet. Yeah. So I think it depends on the students. Also, we have less number of students, so that also helps, I suppose. I think maybe Zoom crashes when you have too many people. That could be one factor. Yeah, I don't know. I haven't faced any issues, but then we have a very few group of students.
Right.
So, yeah.
I know they've been having a lot of security issues too. I've been seeing in the news.
Yeah, that's correct. Yeah, I noticed that, but yeah, I'm not too much worried about uh, those things. Often media, like, so I don't know how much to trust these things also, like, because Zoom is getting so successful suddenly in the last 3 months, its stocks have gone 2.5 times higher. So often they get too much attention.
Right.
And they get a lot of criticism based on that. So I don't know how much valid these things are, but surely it's something to worry about if it is a serious thing. Yeah. So, yeah, I don't know.
Right.
since I think university is having a license with Zoom, presumably the legalities of this from me using this is reasonable. Yeah, often you worry about those things. Yeah.
Right.
Are you teaching any labs?
Yeah, a couple lab sections.
And are you doing the recordings then?
No, I don't do any like a small presentation at the start of the lab like we might do in class. We're not doing any of that. Just Scott will normally record a presentation for the lab, and then we just upload that video onto a D2L for our students to watch, along with a file that shows results of the lab, and then they write the report based on that stuff.
So do you have to explain the video or something? No.
Actually,
Nothing. So you don't meet the students?
yeah, I don't do anything anymore.
Oh, you don't do anything anymore.
I basically just grade the reports, and I still have to create and grade quizzes, but yeah, mostly it's just kind of more just grading, and I'm there if they want to contact me for help, I'm available. But like as far as like actually like teaching the lab, I don't teach lab really anymore.
I see. So it's made life easier in
Yeah,
a sense.
it has actually.
Okay. Yeah.
Yeah.
Oh, that's okay. Yeah. I remember those decisions coming in, but oh, is Angela trying to get in and not able to get in? No.
It showed me something weird at first when I tried to log in at first too.
Tell it again.
When I first went to join the meeting, it gave me a weird message too. I don't know.
Yeah, what was the message you got? This is new in the last few days. I'm seeing it.
It showed up. The screen was kind of gray, and it showed something like the meeting manager or something like that. They call it, what will allow.
Did it say that waiting for the host to give authorization?
Yeah, something like that. So like the host will let you join the meeting soon or something like that. Yeah.
I remember I had set it so that everyone can log in, but in the last few days, Zoom has changed some of the options.
Mm-hmm.
So I don't know how to go back and change it. I was looking at it 5 minutes back. I don't know yet. So the point is that every time someone comes in, I have to manually admit the person. Otherwise, they are put in the so-called waiting room. So there is a waiting room. And I don't know. Yeah. But as of now, Angela is not there. Yeah. She was there in the morning. I had a class in the morning. Yeah. Okay. So maybe start, like it's already 10 minutes. So maybe she's not going to be here. Okay. Oh, so this is so we have an exam, right? So midterm 2. So that's uploaded. And it's due on, I got something. Yeah, I have to admit her now. So now you don't see her. So until I admit her.
Okay.
At least it beeped. So that's good. Hi, Angela. Yeah, okay. I was wondering. No audio from you. Oh,
yeah, I'm good now. I'm good now.
Okay.
Yeah, sorry for being late. My computer the internet was acting out.
Oh, okay.
Yeah.
Okay, but we were just waiting and we just began. Okay. But in the morning also you had problems with the internet, is it?
Morning, and I think it was fine. I got kicked out once or twice, but other than that, it was fine.
Okay. Yeah. Okay, so I was telling I uploaded the midterm too. So I kept changing my mind. Once, remember, I said that there will be a class, there will not be a class. I kept fumbling with that. So here is the final thing. So it has been uploaded. It is due on April 9th, Thursday. Okay. And all the questions are already on the question paper. So no fifth question. Remember, I was telling that there will be a fifth question. I want everyone to be in the classroom. Remember those discussions? So no such thing. Did we lose Angela again?
No, she's here. Oh, she might have frozen. Yeah. Oh no.
Yes.
Man, maybe she might have froze.
Yeah, I think she's frozen. Yeah. Okay. Yeah, she's having trouble. Yeah. Okay. Give her a minute and then we'll proceed. Okay. So this is due April 9th. And you're allowed to take, you can use any resource.
Yeah, something is wrong with my voice. I did it.
Yeah, we noticed that you were gone. Yeah.
Okay. Yeah, just continue. I mean, if it might happen again, if they request for some permission to get to just do that and just continue along, it's fine.
Oh yeah. So did that ask for it again?
Not this time. First time it asked. Not this time.
Yeah, that's a new thing. I don't know how to remove that. So I have to admit you manually. So manually I have to put, so otherwise they put you in a so-called waiting room. Then I have to bring you back from the waiting room to the main room, and I have to do that manually. And again, I think you're frozen. Okay. This is going to be tricky. I just said it a few minutes ago that our internet has not been giving any trouble in this class. Okay. So, okay. So this is uploaded. It's due on April 9th. You can use any resource, but be fair. So that means that don't use outside help. Don't use a help from an expert. That's what I mean. Like it doesn't make sense if someone else takes the exam for you. So that's relevant. Okay, you're back now. Okay. Okay. And what else? Yeah, so there will be a regular class on Thursday. Is that clear?
There is no
So we
virtual
have
exam anymore. Just normal take home.
Yeah, so we are just having a normal take home. There are 4 questions. So there are 4 questions, let's say. Only 4 questions. There is no additional question that will be due on Thursday. So just take home. I made up my mind. And there will be regular class on Thursday.
Okay.
It is due on April 9th, but it is not very strict. But at the same time, it doesn't mean that you can submit it the next week, right? It means that I won't be picky by a minute or 2, right? You can even take few hours extra, but not that you take the whole weekend extra. That's not okay. Reasonable?
So do you mean like does it just have does it have to be by like midnight April 10th? Is that like what you mean?
That's what I mean. Okay, the strict guideline is midnight April 9th, Thursday. But if you were to submit it at 4 o'clock in the morning, that's also perfectly fine. Okay.
Midnight.
Few hours is okay.
So you mean like Wednesday night then? Midnight April 9th.
No, April 9th, 11:59 p.m.
Okay, there we go.
Okay. But again, I don't mean to be so strict about it.
Right.
Okay. So, for example, the internet could be down right then. Take an hour extra, few hours extra, I don't mind, but preferably by early morning Friday. Okay, not more than that. Okay, it doesn't mean that you go all the way off. Okay. So there is a deadline, but it's not very strict.
Right.
You can use any resource, but again, don't ask an expert to take the exam. So be fair to others, that's all. I mean, I think you will be fine. There's a regular class and submit by email. Submit PDF file, a single PDF file, not too many images. Like it's always possible to take JPG images and send it to me. No, it's one PDF file by email. Okay. And is there anything else that might come up? You have a regular class, so you can ask questions at that time. Even before that, if you really think a question is wrong or something, there is a typo. I haven't made the solutions actually, so that could be typos. I just made it today morning. So if there are typos or you really think that you're confused, send me a message. You can use one of those group me's if you want. Did we set that up for this course? Just send me an email. How about that? Okay, and I usually check it often enough, and we have few days from today. There are about 48 hours, so I should be able to answer it. If it is at the last moment, and if there is a really concern, then we postpone it by a few hours for you, whoever is in charge. But in principle, the deadline is set. Okay, reasonable. Any questions you can think of on this, on the logistics of the midterm too? If it comes up again, feel free to contact me. And should I be giving you my phone number? Do you think that will get so important?
No, I mean, as long as you're available, like via email, that's good enough for me.
Yeah, how about this? Yeah, I mean, if you really get desperate, okay.
Well, if you use Teams, I can send you a direct message through Teams as well.
Indirect messages to what?
Like I say, if you use Teams, you can just text people back and forth through Teams. Send direct messages.
This team means the Microsoft team.
Yes.
Okay, yeah, but I don't think I am involved in there, right?
So everybody's on there.
You are there?
Everyone in the university has an account.
So if you send a message to me, how will I get it?
You just have to go into the Teams app.
Oh, so okay, so somehow it will reach me, and then I just have to go there. Okay.
Yeah,
I think we have a group me for this group as well, right? That's what I thought.
Yeah, I created it, but you are logged in, but I think Justin has not yet done it. That's why I didn't. Yeah. Okay. So don't worry about it. Yeah. So anyway, I don't think it will be needed. I like a homework, and in the worst case, we can delay the a midterm too by a day or so, like a few hours or so. Okay. So I think that's my take on it. Yeah. Okay. Okay. So let's. So we were doing electrodynamics in the 4-vector notation. A little bit more, I will talk about that, and then we will go back and do do Maxwell's equations, and then come back to this at a later stage. So remember, so we are doing electromagnetism. Oh, I had to change my board space too. Okay.
I know you probably answered this question, but I'm asking more along the context of the exam questions. Which reference can you suggest, if there is something that you can suggest for the exam questions particularly? I was just going through, and the first and second question seems to be a little bit more conceptual rather than the third and fourth question. And I would like to know if you would give some sort of a specific reading, maybe a book or something.
Yeah, both of them are constructed by me. One of them is based, okay, for the first one, probably the lecture, our lectures. It is recorded now, so you should be able to find it in the recorded thing. That's not a good thing to suggest.
Yeah, but it's again an hour and a half long. I don't want to go back. I mean, I was in the class, so I remember a lot of it, but still, maybe reading
Yeah.
something which might be
So
slightly less time.
Rendler, how about that? I'll use Rendler.
Okay.
Rendler must be the right. But again, it could be misleading in the sense I did not use the book to while making the question. Both the question came up while I was teaching. So it is more based on the lectures that I gave. It is not based on the book. So you may not find it anything close to that in there.
Okay.
But surely in principle, Rendler is the right book to use for that. The third one, what is third one, by the way? Yeah, third one is a magnetic field. Correct. Third and fourth should be there in our textbook. That is Schwinger's book.
Okay.
Okay. Both of them should be there. And in general, just follow the steps. Most probably that should be sufficient, I suppose.
Okay. Okay.
I mean, it is pretty descriptive. I try not to ask too many. I mean, too broad questions in the sense that it's not just one word question. It's broken into a lot of small steps. Does that help?
Yeah.
Yeah, it's all. I find it challenging to answer which book you use. Yeah. So a feedback I need for that is that how much has it hurt in this course that I'm not using a standard book? Like I'm not going by chapter to chapter, section to section. How much does that hurt from a student's perspective?
I don't think much, not really. I mean, most of your class lecture notes has been easy to follow homework wise or for the midterm one as well. So I wouldn't say much, but the relativity is something that I'm not completely comfortable with. This content of a portion of the course, especially when it comes to more conceptual sort of questions. So that's why I just asked for an extra reading.
Yeah. Rendler, I would say, or yeah, this question was, I made this question last year because I was giving a talk in one of those math department talks.
Mm-hmm.
So I made this question for that. So, or the talk got summarized into this question. So that's the way to think of it. But yeah.
Okay.
So,
Yeah, that helps.
Okay. I don't know. So, okay. So electromagnetism. Right. This is just the equations we are rewriting in 4-vector form, and the goal is to see how like position and time come out to be the fourth a form of a 4-vector. That means to say the length of the vector can be got from the time and position together. What is invariant? So similarly, what about electric field, magnetic field, electric current, electric potentials, and so on? And we noticed, or we pointed out, that we can construct a 4-vector or 4 potential, you can call it. This is equal to, this is the usual scalar potential, and that's your vector potential. Right, that's your magnetic vector potential, the electric scalar potential. We constructed a 4-vector associated with that. And then we constructed a field tensor. It's convenient to write it in the covariant form. And this was d mu a nu minus d nu a mu. By construction, it is antisymmetric. That means to say if I were to flip my mu and nu, because of this negative sign here, that will flip sign. So if you think of it as a matrix, its diagonal elements cannot exist because diagonal elements do not change under the interchange of the indices. We showed that as a matrix, this looks like. So we showed this is 0, E1 over C, E2 over C, E3 over C, and then this is minus E1 over C minus E2 over C minus E3 over C. And it's, notice the antisymmetry, it's along the diagonal, it changes sign, and that's B3. B1, and that's 0. So it's minus B3, B2 minus B1. So by putting this in here and using the fact of our definition of electric field and magnetic field in terms of potentials, we could get this. And then we showed that based on this, our Maxwell's equation were the same as F mu nu is equal to, or actually I need to define one more vector. Is it still visible? Yes. So I also had to define J mu, so the 4 current if you want. So this was simply C times the charge density. This is your rho, right? The usual charge per unit volume, and the current per unit volume. The current density is defined as a 4 current if you want. The charge density is a 4th component of the current density. In terms of these quantities, we could write 2 of our Maxwell's equations, not all of them, 2 of our Maxwell's equations, F mu nu. Then notice this is the contravariant form of the field tensor, but we showed that we can move that just by changing the sign. And if I were to put a minus sign here, this will come out to be mu nu times J nu. Okay, that's only 2 of the Maxwell's equations, though. It is not all of the Maxwell's equation. To get the rest of the Maxwell's equation, remember there are 4 Maxwell's equations. To get the other 2 Maxwell's equation, we have to construct another field tensor. Any questions, by the way, on the summary that I wrote from last time? So this was what we covered last time. Again, nothing new in this as far as physics goes, except for the fact that in the context of relativity, what goes with what. That's what the idea is. Like 4 current is charge density plus current density together has an invariant structure as far as the observer goes. As far as a relativistic inertial between different inertial frames, the length of this vector is the same. Similarly, field tensor transforms in a certain way, which we will use today to learn something about the electric fields. Okay, so as a new tensor you can construct, and that is following. Remember your Levi-Civita symbol. This is IJK. This is a completely antisymmetric tensor in the sense that if any one of the indices are the same, it is 0. And if it is cyclic, that means to say 1, 2, 3, 4. If it is cyclic, then it is positive. Otherwise, if it is any one of them is swapped, then it is negative. Similarly, we can define a 4th rank tensor, this time with 0, 0, 1, 2, 3. So this is mu nu alpha beta. So this is a generalization of a Levi-Civita symbol. This is in 3 dimensions. This is in 4 dimensions. So mu nu alpha beta goes from 0, 1, 2, 3. So example is this is 0, 1, 2, 3. This is equal to 1. Right? So this is 1, 0, 2, 3 is equal to minus 1, and so on. Is that clear? Okay. Using that tensor, we can build a new tensor, and that is the following. So this is F mu nu is equal to epsilon mu nu alpha beta times f alpha beta, and this is tilde. This is a new field tensor. Remember, there is electric and magnetic field in this. You will again get the electric and magnetic fields itself here, but now it has been multiplied by this tensor, so it will change its positions wherever they are. Is that clear? Okay, so let's see what are they, what is what exactly they are. So f tilde 0 0 is equal to, the moment I have 0 0, mu nu is repeated, so this has to be equal to 0. Agreed? What about f tilde 0 I? That's equal to epsilon 0 I alpha beta alpha beta. I've already used up the 0, so alpha and beta cannot be 0 anymore. So they have to be either 1, 2, or 3. So it is good to restrict it to Latin indices. So this is 0 I j k f j k. Once I set 0, this behaves very much like our old Levi-Civita symbol. That means that this is the magnetic field. So this means that this is the magnetic field, and since there is an I there, I will call it I's. Okay. So if I were to write this as a matrix, so this is f tilde mu nu. Remember earlier we had the, if I were to show you here, this was having the electric field in it. In this new tensor, the electric field has been replaced with magnetic fields. So this is B1, B2, B3. Right. Since it is antisymmetric, it has to be the same on this side. That's minus B1, minus B2, minus B3. Okay. We can work out the same thing for Ij now. So F0i is there. Fij can also be worked out the same way, and it will come out to be, this will come out to be E3. And it will change sign, so this will be minus E3, E2, and E1. And let me also put the C's there. And it is antisymmetric, of course. Okay. And you will fill this in. Okay, so that's your new stress, the dual tensor. So this is called the, dual field tensor. Okay, Angela, you're still there?
I just switched off my videos. Maybe that might help. Yeah.
Yeah, sure. But you're still there, right?
I'm
that's
still,
it.
yeah. I was gone for
Good.
some time, but I'm still here.
Okay, good. Okay. Okay, so that's your new tensor we have built. That's a dual tensor, and there is one nice thing we can do with this, and that is the following. So let's see what is d mu f tilde mu
So
nu.
I can see that how f of 0i becomes pi, and the the first row and first column elements, but is it obvious how the e terms come in?
It should be. I was jumping that to save time, but let's do it. Okay, let me go on this side. It should be. Let's see. Okay, so f tilde ij, let's say f tilde ij. By this I mean that these are not zeros anymore. Okay, So that's equal to Fij alpha beta, and this is F alpha beta. Okay. One of them has to be 0 because I have set this to be not 0. So one of them has to be 0. So I will need Ij 0k, and this will be F0k, and plus that can be the other term also, Fij k0 and Fk0. Okay. Is that clear? And we know that F0k is electric field.
Okay.
Correct? So this is your, so I move this 0 2 times this side. So that's 0 Ijk, and F0k was minus electric field E of k over C. And plus, so I have to move 0 3 times now. So this is minus of epsilon 0 Ijk and F of k0 again, but this one is the opposite, so it is plus E of k over C.
Mm-hmm.
Correct?
Mm-hmm.
And what happened to the factor of 2? Am I getting a factor of 2 here by any chance? So this seems to suggest that this is Ijk, so this is minus 2 over C epsilon Ijk Ek, right?
Mm-hmm.
And that's because I think there is a factor of half there. Let me see. Let me see.
But then
Yeah,
that
there's a definite good catch. Good. Okay, good that we did that, because then what happened here? So was the same thing here also? Okay, first of all, this definition, I go back a little. Sorry about that. Okay, I think it was, so there's a factor of half here. Okay, we'll come back to this. So that surely makes this correct. So there's a factor of half, and then the factor of 2 is gone. So that's clear now. The electric field, yes, Angela?
Why did we go from step 1 to 2? What is that? How are we doing the 0 for alpha and 0 for beta step?
Oh, I am saying that I and J here are spatial indices. That means to say that 0 is not allowed here. I am interested in this piece right here.
Yeah, okay.
This cannot have 0 in it, right? Because 0th term is this or this.
Yeah, okay.
Right? So I'm saying, so that's why I use Latin indices. Remember that Latin indices do not go to 0, right?
Yeah.
So I and J are Latin, that means it is not involving 0. So if that is not involving 0, and since there are 4 pieces, at least somewhere the 0 has to sit. So it can either sit here or there.
Okay.
Correct? So if I set 0 here, then this is the third component. Like if this is 1, this is 2, that has to be the third one. So 0 or some spatial index with that antisymmetry involved. Is that clear?
Why does K have to be a spatial index? Why can't I take another that is a Greek index as well, like beta?
If this was 0, then it will be 0, right?
Oh, yeah. Okay.
Right,
Yeah.
because of the antisymmetry, it will be 0.
All right, okay.
So so alpha, beta, let's say mu nu, 0 can sit only at one place.
Okay.
If it sits at 2 places, it is 0.
Yeah, okay.
By antisymmetry.
Yeah, okay.
Correct?
Yeah.
So it can only be at one place. So either it is here or it is in the other place. So there's only 2 possibilities.
Okay.
Clear? Helps?
Yep.
Okay. And from that point on, then I moved it to this side to identify that this is actually the usual Levi-Civita symbol. So I moved the 0 to the extreme left. and then I identified this. Is that clear?
Yeah.
Justin with me? Yeah, okay, good. Okay. Okay, so I have to now figure out the 2 there, right? So I think so if there is a factor of 2 here, so somewhere here there is a factor of 2. So this is, oh yeah, I know where it is. So this was, I jumped ahead. Remember, FJK is not exactly magnetic field. This was, so this will be equal to epsilon ijk, and FJK was epsilon jkm times magnetic field Bm. Are you still there? Yeah. Like this was the definition of the field tensor and the magnetic field, right? So the third component. So if this is 1 and 2, magnetic field will get the third piece. Correct?
I think it's BM, or was it B? You written BM or BN? It's
Bm.
BM, right? Okay, okay, yeah.
Yes. Let me. All right. So this is Bm. So the idea is, what I'm using here is that if I were to write it here, so so from earlier, Fij is equal to epsilon ijk bk. That means to say F12 is B3, F23 will be B1, and F13 will be minus B2. Okay.
Okay.
So I can use this then, and this is nothing but 2 times. Like, remember the identity between 2 Levi-Civita symbols, that's 2 times Bm. So that is 2 times delta Km. So this is 2 times Bk actually. Is that clear how I'm doing this? I'm jumping a step here. Let me remind you guys. Okay, let me go back here. So remember, so we have Ijk epsilon jkm is equal to, this is your, how do you do this? Yeah, this is, how about this? I can just write this as Im, right? That's an identity. Okay. Is that familiar? It's not. So Ijk and epsilon Imn is equal to delta Jm delta Kn minus delta Jn delta Km. Is that familiar?
Yeah. Yep.
Right? If that is true, then I set, if I want to get the earlier one, I just have to set, let us say m is equal to j. So let's say m is equal to j. So Ijk Ijn is equal to, I'm setting wherever there is an m, I'm setting it to be j. So this is delta jj delta Kn minus of delta Jn delta K, wherever I see a m, I'm setting it to j. Delta jj, that's 3. So that's 3 times delta Kn. And here j gets replaced, or j gets flapped with n, right? So this is Kn. And that's the same as 2 times delta Kn, which is the statement above, except that some indices has to be changed. Is that clear?
Mm-hmm.
Right. So this one implies this case, and that is a factor of 2 there. And that is what we used here. So F0I, that's still visible. So that's the epsilon that comes up. It doesn't matter whether it is contravariant or covariant, because we are working with the spatial index. It doesn't matter. Because only when the zeroth component comes in, we have to worry about the contravariant and covariant part of this. And that is a factor of 2. And that takes care of this factor of 2 here. Clear?
Yep.
Why is it 2pk? Why is k the indice that survives here?
Oh, why is it the, oh, did I set it? Oh, maybe I did it wrong actually. Hold on. It's not I, because it should be I, right? Yeah. So K sums up, J sums up, I M. So this is I, sorry. Yeah, yeah,
Okay.
good. Thank you, thank you. So that's I. Yeah, it is I. Yeah, good catch. Yeah, yeah. Thanks for, because free index is I, it should be I. Yeah, yeah. Okay. And so that's so good that we did all this, because we caught the factor of 2. I was jumping ahead without that. Okay. Good. So why did we do this? Because now let's see what is, remember your earlier Maxwell's equation was with the d mu f mu nu, which came out to be the current density. But now let's ask, what is d mu f tilde mu nu? That means the new field tensor, where we have, it's called the dual tensor. And what will this be equal to? So let me write this down. So this will be equal to 1/2. I think I block you guys, right? So this is 1/2. Epsilons are just ones or minus ones, so I can bring it out. So it's mu nu alpha beta, and then there is d mu f alpha beta. Correct? So that's just replacing the definition of the dual tensor in here. This doesn't get acted upon by the derivative, because they are just plus ones or minus ones. So the derivative, the 4 derivative, which has either the spatial derivative or the time derivative, acting on the old field tensor, where electric field and magnetic field were in the right places. But now remember the definition of field tensor. So that's equal to 1/2 epsilon mu nu alpha beta d nu, and this is d alpha a beta minus d beta a alpha. What can you say about this? What will this be equal to? Or maybe I should ask a different question, maybe. Yeah, while you think on that, let me erase this part. Any immediate answers as to what that will be? So let me ask a different question altogether in 3 space. So suppose I have I, J, K. Remember, this is totally antisymmetric, right? That means to say that if I were to flap or swap well, I and J's, that comes out to be 0. So let me construct a function J, K, and this acts on some function, arbitrary function. So J and K is summed over. So this must be a vector, correct? So let's call that L of I, right? So some arbitrary vector Li, which is the following. There are 2 derivatives acting on this function f, and it is in an antisymmetric structure that we are constructing. What can you say about Li? What will it be? I've not given you the functional form of that. So that is a very generic answer for this. Use the properties of antisymmetry. Notice that this is antisymmetric in replacement of J and K. Derivatives are symmetric in the replacement of J and K. Correct?
Mhm.
So because of that, this will be equal to 0. Okay, let's see it more explicitly if you want. So let me not even have F here. So this is IJK times DJ dk plus dk dj because of symmetry. Is that clear? This must be true. What this is using is that d by dx of d by dy is the same as d by dy of d by dx. For all standard functions, that's correct. There are sometimes that is not allowed, but then we don't discuss those. I mean, if it has to be an integrable function, I can't pronounce that. If a function can be integrated, that means a three-dimensional function, in terms of three variables, then this must be true. If not, that's not. We don't work with those functions. Of course, one can construct such functions, and that's what happens when you work in non-trivial structures like if you're thinking of a monopole, then you will build such forms. But we are not dealing with that. So this is an allowed statement. If that is the case, then redo this. So this is IJK dj dk, and in the second term, so it's half plus half of IJK dk dj. Now I can use the feature that these are dummy variables, k and j are dummy, so as well change them. So let me call j as k and k as j. So k is j, and I'm replacing j's with k's here, k's with j here. Okay? That is so that I get the same structure as the first term. So this is equal to half. I rewrite this, but down here, I k j dj k. Notice this is almost the same as this, except that I and k are swapped here. So when I swap this, I get a negative sign. And then it is exactly the same term as this, which is 0, right? So that's equal to 0. Okay, that's a one way of showing this, but it is immediate in the sense that this is antisymmetric, that's symmetric, so they cannot get along together. So derivative, any symmetric tensor and an antisymmetric tensor, if its indices are summed over, they will always be give you 0. Okay, clear? That's a very useful statement in general. It doesn't have to be relativity. This is, notice we are in spatial, like this is standard vector calculus. Right? And it doesn't even have to be a vector calculus. This could be any symmetric tensor. If, for example, two vectors, right? This is the idea of why is A cross A 0, right? Why is A cross A 0? Because epsilon is antisymmetric, A is symmetric. Whether I put A in the front or in the back, it doesn't matter. So A is symmetric, but cross product is antisymmetric, so it has to be 0. Right? That's one way of looking at it. Okay. In quantum mechanics, you cannot swap that, so that's why it's not 0. In quantum mechanics, the cross product of two vectors is not 0. Okay. With me till now?
Yeah.
Okay, so if I were to, if I convinced you on that, so let's go back and now look at this, right? There's a mu and an alpha. I can swap that, correct? Here, if I swap it, that's symmetric. Here, if I were to swap mu and alpha, that's antisymmetric, correct? Antisymmetry, symmetry, that's 0. Same thing here, beta alpha, it is symmetric here, antisymmetric there, so it's 0. So this is equal to 0. Okay. Clear?
Yep.
Okay. So if I were to summarize the equations for you guys, so 2 Maxwell's equations, just so that we have it in our head. So we have the first Maxwell's equation given by d mu f mu nu is equal to mu naught j nu. That's your del dotted with epsilon. Oh, there's a mu naught, right? Del dotted with E is equal to rho over epsilon naught. And the second equation is del crossed with B is equal to d epsilon naught E over dt plus vector j, right? Okay, that's your 2 equations, but there is another set of equation, and that is d mu f tilde mu nu is equal to 0, and that's your homogeneous Maxwell's equations. Del dotted with B is equal to 0. Same idea. Why is del dotted with B equal to 0? Because B is del cross A, correct? So this is the same as, let me write that. So del dotted with B is equal to del dotted with del cross of A, correct? Is equal to 0. Why is this equal to 0? 2 derivatives coming with a cross. Like the cross product is antisymmetric. The 2 derivatives are symmetric. They cannot exist. So that has to be 0. Okay, so that's your no monopole statement. So if you were to ever have a monopole, you have to violate that symmetry antisymmetry problem, and one of the ways to do that is to construct a function which is not cannot be integrated in the x and y plane. So there will be a discontinuity along a line. So monopole comes with a lot of complication when you build it, at least if you want to construct a vector potential for it. Otherwise, you give up the idea of vector potential altogether, and then you have some hope. But if you want to write a vector potential for it, then you have a lot of complication that comes with a magnetic monopole. Okay, so that's one of the equation, and the other equation is again an homogeneous equation, del cross E. It's plus P over del T is equal to 0. So these zeros are coming from this 0 here. So 2 of the equations are homogeneous in the sense that there is no source on the right hand side. That's basically a constraint. So these 2 equations are saying that the field has to satisfy certain form. Like that's the idea in here, that F mu nu has this antisymmetry. That's what the information of these 2 equations are. These 2 equations are not really dynamical, they are constraints. In the sense that if you are, in what sense is it a constraint? If you have a pendulum that's going about, there is a radial equation and there is a tangential equation. The radial equation is pretty much a constraint saying that the string, the length of the pendulum is fixed. There is no dynamics going in the radial direction of a pendulum falling. So it's just saying that radius is fixed. Right. Similarly, in that sense, these two equations do not have any dynamics. That is it is more of saying what kind of a field are we talking about. So that's a constraint here on the magnetic and electric field. These two are the dynamical equations. Okay. So that's a summary of Maxwell's equations in 4-vector form. 4 current, tensor fields, and if you want vector potentials. We can add one more statement to it. That is also the idea of Lorentz force in Maxwell's equation. So we also have the Lorentz force, which is opposite. Right? Given the charges, what is the field? We can also say given the fields, what are the forces on the charges? And we know that that's equal to F is equal to Q times the electric field plus Q times V times the magnetic field. If I were to write this in terms of charge densities, instead of talking about a charge, I'll talk about a charge per unit volume. So then I talk about force density, right? Instead of force, I talk about force per unit volume in a space-time. And then it is rho times the electric field plus J crossed with B. Right. So that's the force density. It's not the force itself, it's force density, charge per unit volume, charge times the velocity per unit volume. That's the current per unit volume. Agreed. And then we ask the question, what about this? How does this look like in the 4-vector form? And for that purpose, let's go back and look for what is so let's construct the following. Right. So
Okay, what happened?
Yeah, I don't know. I saw suggest freeze, and then it showed me that I'm the host now. So, not sure what's going on.
Lol.
No idea.
Something is really happening with the internet today.
Yeah.
This hasn't happened in the last couple of weeks to me at all.
No,
Weird.
I don't have this problem.
Do we quit it or does he come back again?
I'm guessing we just hang out. I don't know if he's gonna ask me to let him in since I'm the host. I don't know. I guess I'll just wait for a few minutes. I don't know. Good to see you again, though.
Huh?
So good to see you again, though.
Yeah. Yeah, I just turned it off. I thought maybe that's why my internet is bad. The bandwidth is small, so I just thought maybe it's better if I turn it off.
Right.
How are you dealing with the self-isolation?
It's fine. Like, I mean, the whole doing everything online is working out really good for me. I mean, it's, you know,
You prefer online classes rather than actual one-to-one person classes?
I don't know. Like, I guess I'm good with it either way, but it's kind of nice because I don't know, like our job as a TA is like really easy now. I mean, it wasn't hard
Yeah,
before,
that's
but
true.
now, yeah, it's like super easy now.
I mean, there's that, but you can't go out. Like, it's just weird. There is no change of place, right? It's just the same spot throughout the day.
True. I don't normally stay home most of the time anyways though, so it's not really a change for me. So it's kind of like
Yeah.
no big deal. But how are you holding up?
Not great.
I see.
I live in a studio, so it's like a small apartment already. So
Right.
I'm like in confined in this small place throughout the day, so that's bad. I'm not saying I used to go out much, but at least like you have a change of place, like school in the morning and then like a different place to work out or something, and you just have to do everything in the same little spot. So that's kind of
Right.
it. But I mean, yep. How are your applications coming by?
Application.
Oh, this is still recording, isn't it?
Oh yeah, it is, isn't it? I didn't even notice that.
So it basically made you the host and left. So you have to take the rest of the class now.
Oh.
I'm the student and you have to teach now.
It's not? Okay. All right. Well, I think radiation is coming up. We'll pick up there. Um,
Did you start radiation? Or
right. And yeah, I am. I don't know. I'm not seeing anything like saying he's trying to reconnect or anything. I don't know.
I text him. Maybe I.
This is why I promote Teams. It'd be so much easier to stay in contact with Teams.
Teams? Oh, I have his phone number. Or maybe he's not aware that we are left and he continued teaching.
Maybe.
Well, I cannot make the statement anymore that the internet doesn't go down for on my side. Yeah, so this was my internet that went down. Yeah. Hello, is Angela there or she's frozen now?
Oh, yeah, should we have frozen again?
Yeah, it's not me, right? Yeah, you're moving. Yeah, so your internet is more stable, Justin.
Yeah, apparently. Yeah, it seems to be.
Because on my side, I should say that I think I was just getting lucky because my wife also teaches and she was getting problems. It's just that my window is I was getting away with it.
Right.
So this time I cannot say that. Okay. So Angela, you were again gone.
I was gone, yeah.
Yeah, okay. Okay, so let me try to finish this. If you guys don't mind, can we continue this a little longer today? Like 10 minutes or so?
Yes, okay.
Yeah.
Oh yeah, I got a message from Angela. Yeah, okay. So that's your velocity. So let's look for what the structure is. So my claim is that this is actually the same as stating something like this. So let's see what that leads to. Okay. And I'm just thinking, give me a second. I'm wondering if I want to multiply f alpha beta. Let me just refer, hold on.
When you stopped for a second, I thought I got stuck again.
Yeah, I know. I was I was off for a minute. Yeah, yeah. Okay, okay. So yeah, let's do this, and let's begin by you can read me, right? Yeah. Okay. So let's. So this is. I'm going to define this as f alpha to be equal. So the 4 force, right, is going to be defined. Let me define that, and let me first see what is F0, right? F0 or the zeroth component of the 4 force. What was zeroth component of 4 force? Do you guys remember by any chance? So that had to do with something with do with power, change in energy with time. That is what the zeroth force comes out to be. But I'll rephrase that later once I finish this. So let's identify this first. So this is F0 beta times U beta. But if already this is 0, beta can either take 0 or a spatial value. F00 is 0. So this has to be F0i times U of I. Correct? F0 of I upstairs, that was just the electric field. So this is equal to electric field E of I, right? Dotted, so there's a divided by C, and then dotted with U of I. U of I is nothing but velocity dotted with gamma. So that's velocity. So this is the electric field. Don't confuse with the energy. That also we will talk about. And there is a gamma. Right. So that's your F of 0. Okay. Any questions? Yep. Let's see the spatial components of that. Oh, I shouldn't revise this. So
It's happening again, isn't it? Okay.
I say you gotta freeze again.
it's happening again.
Okay, I thought it happened again, but I think it's okay.
Yeah, I think you're back now.
You got yeah.
So you lost me again for a second, huh?
Yeah.
Yeah.
Okay, I didn't see it. Yeah, I could see you guys, but I might have missed it. Yeah, okay. This is bad, huh? Let's survive. Okay. So F0 is that, but what about Fi? So remember Fi, so there's only spatial index. This is equal. Since I does not have a 0, now beta could be 0 or 0 or the spatial index. So this is F of I times U of j.
I think the best
U of
option.
0 is nothing but C times gamma. F of I0 is nothing but negative electric field. So this is negative electric field over C dotted with U0, since it is in the covariant form. So that is a negative sign. So that is negative C times gamma. And there is an electric field. There is no dot product, right? Because it's a vector on the left-hand side. There is no dot product there. And plus F of ij, remember, is epsilon I j k b of k. And U of j is velocity vector j times gamma. So that's the same as C gets cancelled. So that's V cross B, right? So this is electric field. So gamma times the electric field plus V cross B. Right. There is a factor of Q missing, so I should put a Q in there, right? So I should, so the 4, so since I'm going to identify this as my 4 force, so I'll have F alpha is equal to Q times F alpha times U beta. What about the factor of gamma sitting there? What is the role of that? Remember, 4 force is nothing but rate of change of momentum with ds, correct? But I don't want to write it as ds. Let me write it as dt and then dt over ds, right? With a factor of c there to take care of the dimensions. And that was gamma, right? This was gamma. And that's equal to q times f alpha beta times u of beta. So the two components that we have now is, so if I were to write the 0th component, alpha equal to 0, since the 0th component of momentum has an energy in it, so this is dE by dt. There's a gamma because of the factor multiplying here, and there is a gamma on the right hand side also, if you recall. So this is gamma times electric field dotted with the velocity, and that is a q, sorry, q times the electric field, that's the force dotted with the velocity is your dE by dt. Gamma cancels out, so you have change in energy is just the force dotted with V. If alpha was equal to I, that's a spatial component, this gives you again, this is gamma times the rate of change of momentum with respect to time is equal to gamma times q times electric plus V cross B. So the gammas cancel out. Always what we want to do is, there is a force here that's equal to dE by dt. There is a force here that's dP by dt. So let me rewrite this.
One second, can you not move it? I'm still writing the notes from
Oh,
this.
sorry. Yeah. That is correct, right? I mean, these recordings are not very useful because if you have to go back and refer to it, you have to spend 1.5 hours on this, right? It's not very economical.
Yeah, I'm good. You can move it.
Yeah. Okay. So again, so after all this, what is so if you had to summarize, how do you actually use whatever we did in relativity? The two equations that go about is the 0th component is energy. So this is dE. E is not the electric field. There is no vector. This is the energy. Rate of change of energy with respect to time is force dotted with velocity. Okay. So that's the first equation, and where energy is equal to mc square times gamma. So that's your new definition of energy, kinetic energy basically. Rate of change of kinetic energy is equal to force dotted with velocity. The rate of change of momentum is equal to force itself. So this is your usual old definition, except now the definition of momentum is m times v times gamma. Okay, that's your new definition of force, and this comes as an additional statement. Rate of change of energy is equal to F dotted V. Same old equation, but this energy is no more the kinetic energy. In our case, in electromagnetism, this looks like, in electromagnetism, so this is dE by dt is equal to Q times the electric field. Don't confuse between the energy and the electric field, plus V crossed with B dotted with the velocity. This goes to 0. So we have Q times the electric field. That's what happens in E&M. And the P by dt
Ah, shit, here we go again.
Let's say for the
hello?
Yeah.
yeah, you're back
Okay.
now.
Okay, I thought I lost you guys again. All right.
You did.
You did, you did.
You were going in and out quite a bit, and then it finally went out.
Okay. So did you follow what I was saying until here? Or when did I lose? You lose?
It was like going in and out the whole time you were putting the electromagnetism stuff up.
Okay. So let me, so again, let me repeat what I was saying. In whatever we have done, my primary thing is when we are actually applying relativity to a new problem, we need to use Newton's laws, right? Newton's law stays almost the same as the old Newton's law, except the definition of momentum changes. The same rate of change of momentum is equal to force, but now the definition is mv times gamma. This was also the same equation holds in Newton's non-relativistic case, but now the energy is redefined. It's mc square gamma, right? This is your kinetic energy in relativistic physics. Equations remains exactly the same. Usually the force has to be given to you from somewhere else. The fundamental forces are the gravitational field, Gm1, M2 over R square, or your electromagnetism. In electromagnetism, you introduce this as a Lorentz force, and this comes out to be QE times V, because magnetic field, magnetic force is perpendicular to velocity, right? So that's equal to 0. And this is simply this equation. In your exam, one of the problems, the third question, involves putting electric field equal to 0. If electric field is 0, that immediately goes to 0. Correct? So the change in kinetic energy with respect to time is 0. Okay? Change in kinetic energy with respect to time is 0. Kinetic energy is mc
The
squared.
E in the left-hand side is kinetic energy and not electric field.
No, that's
Oh,
not the
okay,
electric field.
yeah,
That's not the
okay.
electric field. Yeah. I
Okay.
thought I said it, but probably you lost it when I was getting disconnected. Okay. This is not having a vector, so that's energy. And on this side, there is an electric field. There are two very confusing, but I'm trying not to change the letters, because U is usually potential energy. I can use U here instead, but U is usually potential energy. So let's not use that. Okay. Good. So these are the equation that goes through, and if you're, so in your exam, so let me say a few things about what you need for the exam. So if electric field is 0, correct, change in energy, I'm still connected. Yes, okay. So change in energy with respect to time is equal to 0. This implies immediately, because there is mc square gamma, right? And the second equation, if this is equal to rate of change of gamma is 0, that means to say that d by dt of momentum is simply your mass times velocity times gamma can come out, because gamma, derivative of gamma is 0. I can pull that out. That's equal to qv cross b. Okay. If not for this gamma, this is your same old non-relativistic equation. So the question I'm asking in the exam is what changes? Okay, what is the change that is happening? Is there any difference between non-relativistic and relativistic physics? Put the gamma in here, so you can write this equation as dv by dt is equal to v crossed with a new vector omega, where this is the cyclotron frequency, over m. This is what you would have seen in non-relativistic physics, but now there is a factor of gamma that comes in, right? So does the charge go in a circle in the presence of a magnetic field in relativity? Yes, because these equations tell you that they will go in a circle. Okay, so the charge still goes in a circular orbit, right? Velocity is perpendicular to acceleration. But what changes is how many times it goes around in a cycle. This is the frequency, remember, time period. How many times does it go in the circle? That changes. Gamma is greater than 1, so it reduces significantly. So the cyclotron frequency is what changes. So the charge, does it go in a circle? Yes, it goes in a circle, but how many times does it go in a circle, right? So you're going around, the frequency changes. That's what matters. Okay. So that's your help with the exam. Okay. And there is one more problem in the, yeah, so since we are here, I can give you a little help with the midterm. So the other question you have to do is evaluate f mu nu, f mu nu. Okay. So what you do here is there is a sum over mu, there is a sum over nu, correct? So this is fix your mu and sum over nu. So it can be 0. Is that clear what I did? So there was a sum over nu. It runs from 0, 1, 2, and 3. So this is the 0, and that's your 1, 2, 3. Then split your mu also. So this is f0, 0, 0, 0 plus fi 0. So that's how it splits, and then pick terms for the forces, okay, or the field tensors, and substituted it, and you have to find out what this equals. This is an invariant quantity in, it doesn't change between observers, and you have to figure out what that exactly is. Okay. Did that help? Are you guys there? Yeah. Okay. Yeah. Yeah. Okay. We can do a lot more things. We can actually transform electric and magnetic field. But what I'm going to do now from the next class is that I'm going to jump into the Green's function. I will go back to Maxwell's equation and then come back to the transformation part of electric and magnetic field in that context rather than doing it here. Okay. Oops. And if you have any questions on the exam, feel free to contact me on email or something. That could be because I haven't checked it too much for the language and other things. The problems 3 and 4 were constructed like yesterday, basically. So there could be words like there might be typos and those kind of stuff. So if you get confused about that, tell me. Okay. Okay. Thank you. So today the internet was not okay. Yeah.
All right. Thank you. See you again Thursday,
Bye.
right? Yeah.
Thursday. Yeah.
So Thursday
Let's have the class on Thursday.
Yeah. Okay. Cool. Okay.
Yeah. Okay.